Hello everyone, and welcome back to the Pylisnik channel. So, in our last explainer, we really dug into the whole world of IP addresses. Today, we are absolutely taking the next logical step. We're going to tackle the huge question, how does our data actually find its way across the internet? Yep, we are diving deep into network routing.
I mean, just stop and think about that for a second. You click a link, right? And that request has to find one specific server, maybe on the other side of the planet, through this unbelievably tangled web of computers and cables, and it gets a response back to you in the blink of an eye. Seriously, how on earth is that even possible?
Well, the magic behind all of this is a process called routing. It is the absolute unsung hero of our digital lives, the global traffic cop that makes sure every single piece of data gets exactly where it needs to go. To really see how it works, let's start with a really simple problem, a lost letter.
Okay, so to get why we even need routing, let's use a quick analogy. Imagine your computer is your house. You know everybody and everything on your local network. That's kind of like your immediate neighborhood. But what happens when you want to send a letter to a friend who lives in a totally different city? You can't just toss it out the window and hope for the best, right? You have to give it to someone who knows the way.
For your computer, that someone is the default gateway. Just think of it like the local post office for your entire network. It's the one and only exit door for any piece of data that needs to go somewhere outside your little digital neighborhood. And for pretty much all of us at home, that's our Wi-Fi router. And the logic your computer uses? It's incredibly simple. Let's say your PC wants to get to google.com. First, it asks itself, hey, is Google's server here in my house? The answer obviously is no. So what's its next move? It doesn't even try to guess the path. It just bundles up the data and hands it off to the default gateway, basically saying, here, you figure it out. But what happens after that data leaves your house? See, the default gateway is just the very first step. Out there on the big, wide internet, a data packet is facing literally millions of possible paths. So to navigate all of that chaos, every router needs a map, kind of like a GPS for your data. And this map is called a routing table. Every single router has one. It's basically an address book that lists all the network destinations the router knows about, and, this is the critical part, the specific next hop or path to take to get there. It is the brain of the entire operation. Now, the simplest way to get an address onto this map is what's called a static route. This is a path that a network administrator literally has to program into the router by hand. It's fixed, it never changes, and it's absolutely perfect for simple, predictable networks where you always want traffic going to one place to take one specific path.
But, in the real world, especially on business networks or the internet itself, there are often a bunch of different ways to get to the same place. You might have your main, super fast connection, but also a slower backup connection just in case. So, how does the router choose which one to use?
To make that choice, routers use something called a metric. So take a look here. We have two different paths to the exact same destination. One's a fast fiber line, the other is a 4G backup. The router gives each path a cost, and that's the metric. You'll notice the fiber route has a really low metric, just 10, while that 4G backup is way higher at 100.
And here's the golden rule. The router will always choose the path with the lowest metric. Always. The metric is just a number that represents the cost of using that path. It could be based on speed, reliability, maybe even actual monetary cost. Lower is always better. So in our example, all the traffic is going to flow through that fiber connection because a metric of 10 is way better than 100. Okay, so manually setting up static routes, that's fine for a small network. But the internet has almost a million routes, and they're changing all the time. You just can't have people updating all of that by hand. It's impossible. So we need a system where routers can build and update their own maps automatically. And that system is called dynamic routing. Routers use these special protocols. You can just think of them as languages to talk to each other. They're constantly sharing updates about which networks they can reach and how good the paths are. If a connection somewhere goes down, they tell their neighbors, and everyone updates their maps on the fly. This is what makes the internet so incredibly resilient. And there are a few different languages they can use. One of the oldest is RIP, which is super simple. It basically works on rumors. Each router just tells its immediate neighbors how far away things are. A much more modern choice for corporate networks is OSPF. With OSPF, every router builds a complete detailed map of the entire network, which makes it way faster and more efficient. And then you have the big one, the protocol that runs the internet, BGP.
It is built for massive scale, connecting huge service providers and making decisions based not just on speed, but on business policies too.
All right, so we've covered a lot of theory, but where do you actually see all this routing stuff in action? Let's bring this back down to earth and look at the real-world hardware and some practical examples.
So, the most common routing device is the one that's probably sitting in your house right now, that little box that gives you Wi-Fi. Now, in the corporate world, you've got much more powerful dedicated routers, and you also have this cool thing called a Layer 3 switch, which is basically a high-speed switch that has learned how to do routing. It's perfect for handling traffic inside a big office building. Now hey, remember our previous explainer on VLANs? We talked about how you can create these separate virtual networks, right? Like one for the sales team and another for marketing to keep them totally isolated. Well, by default, a computer on the sales VLAN cannot talk to a computer on the marketing VLAN. They're on completely different islands.
So, how do you connect those islands? Well, that is a core job for a router or a Layer 3 switch. It acts as the bridge. It connects to both the sales and the marketing VLANs, and using its routing table, it can intelligently forward traffic between them, letting them communicate and share resources, but in a totally controlled and secure way.
And just to give you a sense of the sheer scale we're talking about, remember BGP, the protocol that runs the internet? Well, the global internet routing table that all the major routers have to manage contains over 900,000 unique network routes. And that number? It's growing every single day. It's just a staggering amount of information being managed in real time.
When you really boil it down, routing isn't just some technical feature. It's the very fabric that stitches our entire digital world together. It's what turns a bunch of isolated islands into a single, global web of information. So, I'll leave you with a final thought experiment. We've seen just how essential this whole process is, but just imagine for a second that it all just vanished. What would happen if every single router on the planet suddenly forgot its routing table for just 1 minute? Every website, every email, every video stream, every online transaction would just stop. Dead. It would be complete and total digital silence. That's just how fundamental routing is to our connected world. Thanks so much for tuning in, and I'll see you in the next explainer.